Hello, I'm Ben Jenkins from the University of Oxford, and today I'll be talking about the automated and reproducible detection of edge clusters in atom probe datasets. Why are we interested? Well, small solid clusters, such as those shown on the right-hand side here, can have a large impact on the macroscopic mechanical properties of many material systems. Atom probe is well suited to characterizing these small solid clusters in their early stages of formation. However, there is a desire to create models which can quantitatively relate changes in the nanostructure with changes in the mechanical properties of materials. In order to do this, it is very important that atom probe data is accurate, reliable, and reproducible. One problem with atom probe is that it samples a subvolume of the material, and this can lead to features which intersect the edge of the atom probe volume not being wholly contained within the dataset. For the purpose of this presentation, these will be referred to as edge clusters. Now, edge clusters can bias both size and compositional measurements. Here, on the schematic diagram on the left, we can see that this feature would be measured as having 100% nickel and a thickness of a certain size. However, in reality, this feature contains copper and is also larger than measured in the atom probe experiment. We can identify these edge clusters manually in the case of having very few features. In the example here, we have two features which we can clearly say are edge features and two which are wholly contained within the data. However, we can't do this manually to all datasets, and the reason is that in many real atom probe experiments, we can have many hundreds of clusters in a single experiment. So doing this manually would take a lot of time, and also it's incredibly subjective and will therefore lead to significant user-to-user variations and affect the reproducibility of results. So what we need is a tool that can accurately and reproducibly identify these edge clusters in an automated fashion. So how are we going to overcome this? Well, firstly, we need to define the edge of our dataset. We then need to determine if a cluster is wholly contained within this dataset or not. We then need to account for these clusters in our calculations and hope that this will then lead to improved measurement accuracy. The first stage is we're going to define the surface of our reconstruction. And to do this, we're going to implement the alpha hull algorithm. This generates an alpha shape around a point cloud, and this is advantageous as they can contain shapes which are convex in nature. This is preferred for atom probe datasets due to the complex shapes, possibly with reentrants, that often occur. And on the right-hand side here, we can see how an alpha shape can accurately capture the shape of the 3D point cloud from an atom probe tomography experiment. The second stage is we need to determine if clusters lie within the volume. And we could do this by testing every ion in each individual cluster to see if it lies within the alpha shape generated in stage one. However, this is incredibly computationally intensive, and a smarter and quicker solution is to create a convex hull around each cluster. And then we can simply test the points that make up the vertices of this convex hull for each cluster and perform a simple in-out test. If all of the vertices of a cluster lie within the alpha shape generated in point one, then we would determine that the cluster is a non-edge feature. However, if one of the vertices lies on the alpha shape generated in stage one, the feature would be described as an edge cluster. We can then use this information to improve calculations. So firstly, we could look at the simulated dataset. So we generated many thousands of these datasets where we knew the size, number density, volume fraction, and composition of the features. What we can see in this graph on the right-hand side is that if we include the edge clusters, which are shown in green, then our size measurements are biased. And actually, we ended up measuring a size which was 17% lower than the true size of the features. The same can be true of the composition, where the composition of the features sometimes contained 0% core ions, and this was due to just the shell of these features being contained in the reconstructed volume. And then when we look at the number density measurements, what we can see is that the true number density is shown by the blue line here. And if we include all clusters in the number density measurements, we overestimate the number density of features. However, if we identify edge clusters and count them in our calculations, we get an answer which is much closer to the true value. This leads us to ask, can we use it on real data? And the answer is yes. This here is a neutron irradiated steel, and we can see that the clusters were detected, and we can see the edge clusters here in red and the non-edge clusters in blue. Now, the code for this is available online at GitHub, so anybody can use this. And there are further details in our paper, which is also available online. So to conclude, edge clusters bias experimental measurements in atom probe tomography datasets. However, they can be automatically and reproducibly identified using alpha hulls. This leads to an improved accuracy of quantitative results and can be implemented by other researchers. With that, I'd like to thank you for your attention, and if you have any questions, please email me on the below address. Thank you.